So now we got some intuition about what it means. We're going to play the game, right? So this one, well, I guess I'm going to do a formal, right? I write the proof in different ways to make people, but it's all boils down to the same, right? We read this left to right, right? We're trying to prove for all x. So let x for all be arbitrary, right? Why did I put the for all down here? To emphasize the fact that it's an object, and I made it red because it's an object given to me by the adversary. It's not a generic variable x. It's a specific red mean object, right? And the reason I put the for all in there, in fact, my first slides didn't. It just made it red. But then I realized on a test, you don't have red, right? But you have for all, right? Everybody good with that? Right? And here I could say, oh, I didn't say it, but you could have written down here to make me a little happier, provided by the adversary, right? All right, and now I come in and I say there exists the y. So then I have to come up with a y, right? But my y, I already know the x. So my y is a function of your x. So I say, I'm going to define this object y as a function of my adversary's x, right? Right? It depends on what comes before. And then your algebra, you just say yes, right? Everybody got that? Right here, I did do a little algebra. I plugged it in, and right. Everybody good with this as a proof? Can you do this on the test? Can anybody not do this on Wednesday? Because it's on the test. All right, right. So then you can conclude somehow, right? The prover can always win, so the statement is true, right? Right, and then we could even say, what does it mean? Every real number has an additive inverse. All right, so I guess we skipped down to this one for some reason, right? Says exists, exists something, right? We read it left to right. There exists the y, so x, there exists the y. So I have to come up with a y, right? So I should have already known what it means to know what y I need, right? There exists an, right? Something, what was it, an additive zero, right? Right, nothing comes before it. I'm going first, so it has to be a fixed value, right? And then, right, so then we can continue our proof like this, right? Is that a good proof? You see, the angry guy means it's not a good proof, right? If you and I were standing on the subway, maybe this would be good enough, right? But since what we're teaching here, what I'm testing you on is, do you play the game? Then you better play the game, right? I'm the boss. Everybody good? So this isn't good enough. I say, what is x? Where did it come from, right? So we have to say, we have to now come up with the for all x. So let this be arbitrary, right? And then we do it, right? I'm just putting in an extra line because what I care about is not the algebra. What I care about is the game, right? Everybody good? All right, what about this one, right? We skipped this one because this one's false, right? So order really matters. It says, what do? We say, oh, sometimes, in fact, if you saw what I wrote last night, it says, if it's not valid, if it's not true in every model, try giving a formal proof and see what goes wrong, right? And so maybe we'll be doing this here, right? I'm supposed to come up with a y, but I don't know which one, right? I'm lost already, right? right? So right now I'm kind of keeping it open what it might be because I don't know, right? In fact, if you're trying to prove it, you know you have to say let y be, but oh, I don't know what, so I'm going to keep going and I'll fill it in later. That's always a useful technique, right? Right? In the 0, 1, you could say let it be, I don't know. You come down to the algebra and you say, oh, it's 0, and you stick it up, right? So that's kind of what we're doing here is we're hedging our bets. We don't really quite know what it's going to be. Then we have to come up with an arbitrary thing. Then we have to say the adversary is a Forall, so the adversary comes up with something knowing mind, right? What does the adversary do? The adversary is smart. In this case, we know what he's going to do, right? Right? It's arbitrary, but he's going to give us some worst case thing, right? And then, oh, it's not 0, right? Oh, here he gave us negative y plus 1, right? Why did he do that? Because he was messing with us, right? And then you plug it in and you say, oh, it's not true, right? Yeah? It's kind of proof by cases, but we have an infinite number of cases. There's still, I don't think, actually somebody said proof by cases. You can't prove this is false by cases because there are too many cases either way. In fact, I'm producing here, what I'm trying to do is seeing where this goes wrong. And you know where I'm going is I'm turning into a proof that it's false, right? Right here, look at, I just gave you a proof that it was false, right? We turn this to a Forall. I came up with an arbitrary. This turns to an exists. I came up with a specific thing, right?
Professor, I have a question. Professor?
Yeah, just wait. It's the game. I wouldn't say it's by cases. It's by the reverse game. Yeah? God?
So can you go back a couple of slides? When you were working on this one, I don't exactly understand why you said that, like you kept saying like you didn't like the way it was done, and I'm kind of confused why.
Oh, let's go. Where was that one? Where did we have our devil? Here. This one I didn't like because I don't know where X comes from, right? If I saw a mathematician doing this, I would know that he knew that X was an arbitrary value, right? And he was sloppy, and I would forgive him. But I'm not so forgiving to you because that's what I'm testing you on. All you have to do to fix this is add the line 2. Right? I'm going to assume that's a right. All right, so where are we? We're now, so if we take the negation, oh, here, there's the negation already, right? You take the negation, and that's, right? We keep doing it. That's the negation, right? Everybody got that? And so one way to prove that something is false is to prove the negation, right? So it's the exact same proof. We've just switched. Now for all, we switched the colors, right? Now it's arbitrary, right? Now there exists, so we come up with this, right? You see, I'm just showing you that it's the same. Right, everybody good with same? All right. All right, here's one what we got. So let's go back to the algebra question. If this was an algebra class, we would start by saying, you know nothing about the reals except what I tell you, right? Because you might be wrong, and our goal is to prove things about the reals. So we start with as few assumptions as possible, right? So let's start with this assumption that everything has an additive inverse, right? Let's start with this assumption that if you add 0 to anything, it doesn't change it. And let's do this assumption, which says if you know A equals B, then you can add C to both sides, right? Everybody see how those are? We're going to assume those are true. And what do you want to prove is that if you know that this is true, you can cancel C on both sides, right? And you might say, this is obvious. Yeah, but we prove obvious things, right? All right, but first off, let me give you some counterexamples, right? 2 plus infinity does equal 5 infinity, right? So there's a counterexample. So you have to know that we don't have an infinity, right? Here's another one, mod 6, if you know how to work mod 6, right? 2 times 2 is 4, still mod 6. 5 times 2 is 10, which is 4 mod 6. These are equal mod 6. But 5 and 2 are not, but here we, right? But 2 and 5 are not equal mod 6, right? So here's a counterexample. And why is this a counterexample? Because over mod 6, we don't have division, right? Now, over a prime field, we have division, but over mod 6, we don't have division, right? So we're kind of have to use the fact that we can subtract. Why can you, if you were in grade high school, why can you go from this to this? Why? Because you subtract C from both sides. Well, that requires that you can know how to subtract. Yeah. Don't worry about it. It's a counterexample. It's a world different than the reals in which you can't divide. That's all you need to know. It won't be on the test. All right. So how do we prove it? Right? We first state what we want to do. And remember, why did I got A, B, and C here? It's because they don't all fit. Right? Just assume, oh, here I've labeled them. Right? All right. So then our assumption. And then now we say what my goal is. Am I right? My goal is to prove B, D, right? So how do I prove D? Is I got a Forall here, right? So I let these be arbitrary, right? Remember, this is a good advice. Don't get worked up about doing anything with your assumptions. Go for what you want to prove, right? State you have these assumptions, right? So in any proof, you're going to state you have your assumptions, and then ignore them and start going in for your proof. And when you get stuck in your proof, go up and see which assumption will help you. All right? So here, I need to prove for all, right? So I let these be arbitrary, right? And so somehow, this is just saying, I have a little subroutine. Somehow I have to prove all of this, right? Now, how do I do that? We'll leave it to later. It's a lemma, right? And then I get what I want, right? Everybody see that? Right, so now we're doing this. And why did I do this? It's because the whole thing didn't fit on the page, I think. All right, so now we're going up here, right? Our goal is to prove this. Well, my assumption, here we had an assumption somewhere. All right, so we're trying to prove it by deduction, right? So we assume the left, right? And then this tells us, right, what do we need? We need to come up with the inverse of C, right? We want to, what if you're in, I mean, if you're in high school, what do you want to do? You want to cancel the C's. How do you, but we only know how to add. So what do we add? We add the inverse. So how do we get the inverse, right? We have to say, oh, A, talk to A. I give A a C, and what does A give me? A negative C, right? She gives me negative C. Everybody agreed? Here you got, see my little notations here, right? Because this I got from the adversary, and this she's giving to me, right? And so then I say, great, what is the oracle telling me about these? She's telling me that they add up to 0, right? All right, so then, right, this just says, oh, now we go over to C, right? C says that we can add our negative to both sides, right? We have our negative, we want to add it to both sides. So I give her the A, B, and C, which are these, and we add C to both sides, right? See that? So that allows me to do that, right? I knew, right, here I knew this piece, so I can add C to both sides, right? Everybody follow this? So now what do I want to do? I'm going to add these and get 0, right? So I use the fact that the sum is 0, and I do that, right? I just cheated. Anybody notice the cheat? I moved the brackets on the plus, right? We needed to know here what we really have is this, and I've changed it to this, plus this, and this, right? So anyway, we cheated there. Everybody got that? Right? And now what do I need? I need to prove this. So I have to prove that the 0 doesn't do anything, right? Who helps me with that? B helps. I go up to Oracle B. I'd say, hey, something is true for all x, so it should be true for my A, and it should be true for my B, right? So we get what we want, right? Everybody see this? And this is what you do if you took a formal course in algebra, right? Are people dying? Yeah. Oh, if you didn't notice the cheat, don't worry. A plus B plus C. Is this the same as this? Yeah, there's a word associative. I should have put in here the associative rule. I skipped it. I didn't say something that was false. I just assumed something that we didn't write down. Right, everybody good? All right. Okay, this is something we did in 1019 that everybody struggled with. All right. So let's define our superscript greater or equal to be all the reals that are greater than or equal to 0. Right? Here they are. They're in orange. Everybody agreed? What is the minimum value in this set? Well, everybody would say it's 0, right? Why is it the minimum value? Because for every object in the set, it's bigger, right? And it's in the set. Everybody with me here? We write it down. For every object, for every y in the set, y is bigger than 0, and 0 is in the set. Hence, it's the minimum, right? Anybody disagree with this? This is the definition of minimum. All right. Why there is a minimum? Because there exists an x such that for all that there exists an X in the set, such that for all Y in the set, the Y is bigger or equal to. Right? Everybody got definition of minimum? All right. Here's another set. It's the set that are all bigger than Y, bigger than 0. It doesn't include 0. All right, let's test you all. What's the minimum of this set? How many people say it doesn't have a minimum? How many people have no idea and think this is a horrible course? All right. All right, what's the minimum? Right? It can't be 0 because it's not in the set. Can't be 1 or this because they're smaller things, right? We're doing reals, not integers, right? Right? You could say, well, it's like this, but with an infinite number of zeros, right? That doesn't work for me, right? Maybe it doesn't have a minimum, right? So if we negate this, it says for everything that you want it to be a minimum, everybody in the set, there's somebody that's bigger. Oh, there's somebody that's smaller, right? Everybody good? There's no minimum. Why? Because you give me somebody in the set, I can give you somebody smaller, right? We're saying every fixed X fails to be the minimum, right? So how do we prove it? Well, it says for all X, so let X be arbitrary, right? And sometimes I use the notation and sometimes I forget, or sometimes I made these slides earlier, right? Now, then it says, read it left to right. You give me an arbitrary X. I have to come up with a Y, right? What's my Y? Half of X, right? Now, we're assuming that people know how to do algebra, right? So then you say, what about Y? Well, it's in our set because it's bigger than 0, and it's smaller than X. So we're done. All right, everybody good? All right. 0 is not the, okay, we're going to do more math, right? 0 is not the minimum, but it's special, right? I mean, it certainly has something to do with this set, right? Now, -3 is smaller than everything in R, right? So is -1. What is 0? It's the biggest number that's smaller than everybody, right? Right? So it's called the infima. In fact, I had to look this up. I knew the word supremum, but I didn't know the word infima. Right? It's the biggest X such that everybody in R is bigger than it. Right? Which is 0. Right? Everybody good with that? How are you doing with these? This is exactly the type of thing we're going to do in the test. Right? I'm going to give you some statement like this. And if you have some mathematical understanding of it, maybe that'll help you, right? But certainly when we took 1019, half the class was convinced that this set had a minimum, right? So even if you don't know anything, just bang out the proof. And if I'm giving you the proof, if I'm giving you this question, know that I believe if you just bang it out mechanically, you'll get the right answer, right? So do not panic. Just bang it out, right? Now, where does it get hard is when you need to construct something. You have to be creative in how to construct it. But you could always leave it, right? Let's go back to this proof, right? Oh, how do I come up with this? Well, you leave it for a minute and you say, well, I need it to be an R and I need it to be smaller than X. What has this property, right? You can do it, right? Oh, how much time do we got? We got enough for calculus? 4 minutes. Let's see what we can do. You take any calculus class, they do epsilon delta proofs. How many people have done an epsilon delta proof in their life? Did you understand it? All right? My belief is they don't teach you it, right? Right, so here, for all epsilon, epsilon is your worst case thing bigger than 0, small as possible. There was Leibniz and there was Newton, both invented calculus. One of them did limits, which is kind of like Forall, and the other did infinitesimals, right? So what is an infinitesimal? It's a number that's bigger than 0, but so small you don't know what to do with it, right? But we're not doing infinitesimals. We're doing an epsilon given to us by an adversary, all right? Now you give me your worst case epsilon, and then I can give you a counterexample with delta, all right? So it's a competition, right? So here, there's some function, and I want to prove that it's continuous, right? What does it mean? It doesn't, you change x a little bit, it doesn't change y very much, right? For all x, it's continuous at x. All right, great. What does that mean? Right, so then he says, I'm not convinced. It does change. It's not fixed, it changes, right? So here's f of x, and you go somewhere else, it has a different value, right? All right, yeah, I say, I'm not saying it's constant, I'm saying it's continuous. All right, well, what does that mean? Okay, we'll allow some change, right? How much change am I going to allow? Well, your x prime is way too big. That's too much change, right? How much change am I going to allow? I'm going to allow epsilon change, right? You can make the adversary can make the allowed change as small as possible, right? I'm only going to let you have an infinitesimal change, a little change, right? But he has to give you a concrete epsilon, right? It gives you a concrete epsilon, which is the allowed change, right? And then, okay, I can do that, right? So, but the key is, once you, right? Right now, so I'm going to counter. I will keep my function within epsilon, but I'm going to come up with a delta, and you need to keep your need to keep your x within that delta, right? So, all right, right. So I say you got to keep your x within the delta, and as long as you do that, we're good. So he says, what does that mean? All right, I can come up with any x prime that's within that delta, right? And that says, great. If you give me an x prime that's within your delta, I will assure you that my f doesn't change by more than epsilon, right? Everybody getting this game? Right? Are you guys good? Right? Right? You give me, here's the picture. You give me any x prime in there, I prove that f is in there. You can see how there's a lot built into this game. Right? So let's do it. Let's prove that x squared, the function f equals x squared, is continuous. Right? Here's the statement. Right? I want to prove that it's continuous everywhere. So you give me an arbitrary amount I'm allowed to change, and I'll give you a delta in which you can change your x. Right? All right, so don't panic. Remember, don't panic. Play the game. So how do you play the game? Let x be arbitrary, right? Let epsilon be arbitrary. Let x delta be, all right, I don't really know the value left now, right? Remember I said I don't really know, so let's leave it for now. It's something, and it's some function of epsilon, right? then, well, we need x prime to be within delta. All right, great. So then we have to go through and crunch out the proof. And we see, what do we need? Oh, I can make a delta to make it work. Right? Does that make sense? And that's what we got. Right? Now, what about this? Is this continuous? No. So we take the negation. And what does the negation say? I give you, where is it not continuous? It's not continuous at 5. Okay, there exists an epsilon. Well, the gap here is 0.0012, so I make my epsilon 0.001, right? You make delta really, really small, all right? I can come up with an x that's within that delta of 5, and your gap's too big, right? Everybody good? And I think we're out of time.